14.3 moving graphs around. Here are equations and graphs that represent 5 absolute value functions. Notice that the number 2 appears in the equations for functions g, h, j, and k, so not f. Describe how the addition or subtraction of 2 affects the graph of each function. Well, the thing that I notice that sticks out to me right away is that this point of vertex has been shifted in every single graph. So here, I would say it's gone 2 to the right. Here, 2 left. Here, 2 down. And here, 2 up. So all shifts of the vertex. Then, think about the possible explanation for the position of the graph. How can you show that it really belongs where it is on the coordinate plane? Well, this is very much like the equation for a parabola. If you remember, vertex form for a parabola. If you remember vertex form, it was y equals a times x minus h squared plus k, where h comma k is the vertex. If we look at these graphs, I can see that the vertex here is at 2, 0, negative 2, 0, 0, negative 2, and 0, 2. All right, so this form actually is pretty much the exact same thing as a parabola. We can even keep the a in front. I'm not going to really do that because you may see someone making an absolute value function wider or more narrow. That could totally happen. So for absolute value functions, this is sort of like vertex form for absolute value function. This value a can make it more wide, more narrow. Right, can increase the slope and decrease the slope. Here is our horizontal shift. And k right here is our vertical shift. We can also say here that h comma k, that's where the vertex is. All right, so it's very much the same as the vertex form we dealt with the parabola. Okay, are you ready for more? Mark the minimum of each graph in the activity. Each point you marked resembles the least output value of the function. Right, we know that to be the vertex. Right, vertex is a minimum or maximum. In each function, what value of x gives that minimum output value? Well, we can see here the minimum, the x value of 2 will give the output value. All right, and we see that 2 right there. Here we've got negative 2. And really, even though that says positive 2, remember the equation for our function is x minus h. So if I put a negative 2 in there, it's going to be negative 2, which is just equal to 2. 2 down, so that's minus 2. 2 up, that's plus 2. The k value is what it looks like. That doesn't change. 2. Another function is defined by m of x equals the absolute value of x plus 11.5. What value of x produces the least output function of m? Be prepared to explain how you know. Well, this one we can see is that horizontal shift. So if I look over here, remember it's that number you see here. If I'm subtracting it, right? I'm subtracting 2. That means my minimum output of x is, my minimum value of x is 2. Here I've got positive 2, really negative 2. Here, I'm not subtracting anything. So really, I'm subtracting 0. And the x value is here as 0 as well. So if I got plus 115, that's really like saying x minus negative 11. Did I say 115? X minus negative 11.5. So that's going to be my minimum value of x. or at least the x value that produces the minimum value. Right, x value that produces. Because when they talk about the minimum, they're talking about how high or low it is, or in this case, how low. So that's talking about a y value. So we're seeing what x value gives me the lowest y value. What x value gives me the vertex. All right, sketch a graph of M. All right, well, I know that it's going to be at negative 11.5. So that means like probably somewhere over here. And then we know it to look like a V, or standard absolute value function. That's all for 14.3.